Right. Next let us take up the example of damped simple harmonic motion, and the idea is the following. If I look at a simple harmonic oscillator such as a mass and a spring connected to the mass and the simple harmonic oscillations of this mass, we have seen that the equation of motion of this mass, Newton's equation, is mx double dot equal to minus kx, where k is the spring constant, or x double dot equal to minus omega squared x, where omega squared is k over m here. Now this motion goes on forever for any initial conditions, because there is no mechanism by which energy is dissipated. The energy of the spring of the system is constant for any given initial conditions, and if you recall, the phase trajectory in this case in the x dot x plane, this phase trajectory was in the form of ellipses for any given energy traversed in the clockwise sense here. There is no damping or dissipation in this system. This oscillator goes on forever, and that of course is unrealistic. In any physical oscillator there will always be a mechanism by which some loss of energy is incurred. The system comes to a halt either by friction or by some other damping mechanism, and we need to incorporate that in our understanding of simple harmonic motion. Basically what happens when you include the effect of such dissipation on this conservative motion. Okay. Now this depends on the model, this depends on what kind of friction we have, what is the precise mechanism by which this friction dissipates energy and so on, but a very simple and standard model which is applicable in a large number of physical situations is the following. It is exactly what happens when you drop an object like a ball bearing inside a dense liquid. What happens is, due to the viscosity of the liquid, the particle's velocity gets slowed down. There is friction on this object because of viscosity, and there is what is known as viscous drag or viscous damping, which causes slowing down and dissipation of energy. Now just as when you walk through a crowd, the faster you try to go in a particular direction, the more the retarding force, because the more the number of collisions from the front. In exactly the same way, the viscous damping in its simplest form is a drag force which is in the direction opposite to the direction in which the velocity is directed, or opposite to the direction of motion, and is proportional to the velocity itself. So the very simplest model that we can put in for damping here is to modify this equation, modified to x double dot equal to something which is proportional to the velocity. Of course there is this restoring term, still the spring force is still there, but there is also a term which is in the direction opposite to the direction of the velocity. So it is proportional to minus x dot times some constant, so minus some gamma x dot, and this gamma is the damping constant or the friction constant. Notice from this that gamma is actually a physical quantity of dimensions the same as that of frequency, T inverse. So the physical dimensions of gamma are those of inverse time, the same as those of frequency. Okay. So what I have done is to really take this equation and rewrite it in the form mass times the acceleration equal to minus m omega squared x minus m gamma x, and cancelled out the m on both sides in order to get this equation. So this standard equation of the form mx double dot plus m gamma x dot plus kx, if you like, equal to 0 is the standard equation for the damped simple harmonic oscillator in one dimension, where this is the damping constant and that is the spring constant. and that is the general equation. So, anything which is of this form, any second order differential equation of this form would be that of the damped simple harmonic oscillator. So, this is the damped SHO equation. And a little later we will look at an electrical analogy for this mechanical damped equation, but before that let us try to look at the solutions of this equation here. Earlier I mentioned that this equation was entirely equivalent to saying that the total energy E was equal to 1/2 p squared or x 1/2 mx dot squared plus 1/2 m omega squared x squared equal to a constant of the motion. That is no longer true. So, this was a constant of the motion, and that is what led to this ellipse as the phase trajectory. Such an expression for a constant energy is not available in this case. This equation is not consistent with saying that the energy given by this expression is a constant. In fact, energy is not conserved in this problem, as we will see in a minute. I ought to mention here very carefully that gamma is greater than 0 because the friction is opposed to the motion, to the direction of the velocity. So, there is a minus sign and then a positive constant times x dot there. I have chosen that constant to be gamma. Actually I have written m gamma in the equation of motion, taking out an m simply for convenience, so that gamma has the same physical dimensions as omega, and the idea, as we will see shortly, will be to compare the relative magnitudes of gamma and omega. That will control the nature of the motion here. How does one solve an equation of this kind? Well, there are standard methods for solving such a second order differential equation in elementary calculus, but what we need to do here is to write down the solution based almost on inspection. It was clear here that the solutions were e to the plus or minus I omega t. So, some kind of exponentials, and one tries the same thing here, because what happens when you have a linear differential equation, and this is linear because there is a first power of x here, first power of x dot and a first power of x double dot, is to notice that if you take a quantity like e to the lambda t, where lambda is a constant, and you differentiate it once, you bring a lambda down. You differentiate it a second time, you bring another lambda down, so that the operation of differentiation becomes equivalent to the operation of multiplication when it acts on e to the lambda t. So, that suggests immediately that one tries a trial solution x equal to some constant, because this is a linear equation, multiplicative constants will be fixed later on by initial conditions, equal to e to the power lambda t, where lambda is as yet undetermined. If you do that and put it in here, as I said, each time you differentiate with respect to time, you bring down a lambda. So, it says this equation simply says lambda squared plus gamma lambda plus omega squared equal to 0, because this whole thing is multiplied by e to the lambda t, and that must be equal to 0. I have now taken out the m and written k over m as omega squared, so that you have two constants gamma and omega squared in the problem. Lambda is unknown as yet, but it has to satisfy this condition here for all t. Since e to the lambda t is not identically equal to 0, this can only be done if this bracket vanishes. So, this implies that lambda must be such that lambda squared plus lambda gamma, which in turn implies that you have two possible values. Lambda can only be equal to lambda 1 or 2, which are given by minus gamma plus or minus square root of omega gamma squared minus 4 omega squared over 2. These are the two possible roots of this quadratic. So, it says that a trial solution of this exponential form is admissible for this equation, provided lambda is not arbitrary, but can take on either this value or that value, one of the two roots here. one or both of these values here. And since this is a linear equation, this equation is a linear equation, if I find one solution and I find another solution, any linear combination of the two is also a solution. So the most general solution of this equation, this would be of the form x of t equal to some constant times e to the lambda 1 t, let us call it C1 for the moment, plus some other constant e to the lambda 2 t. That is the most general solution, where the constants C1 and C2 have yet to be determined, but the exponents, the coefficients lambda 1 and lambda 2 are determined in terms of the parameters in the problem, namely gamma and omega, by these formulas here, these expressions here. These are the only possibilities for the general solution. But as soon as you see this, let us rewrite this a little bit more simply. So let us rewrite this as plus or minus in this form. It is immediately clear that three possibilities arise, three distinct possibilities arise depending on the relative strengths of gamma and omega. So the first thing that arises, the first case 1 would be the case where this number is bigger than that number, which means omega is bigger than gamma over 2. And that physically corresponds to the case where you essentially have an undamped simple harmonic oscillator with natural frequency omega, and the friction constant is small compared to the natural frequency, or the natural frequency is bigger than half the friction constant here. That is all that is needed. Omega must be greater than lambda over 2. So 4 omega squared is greater than gamma squared, which will immediately mean that lambda 1 comma 2 is minus gamma over 2 plus or minus I times omega squared minus gamma squared over 4, and remember this is a positive number. So we have a pair of complex conjugate roots with a real part which is non-zero and an imaginary part which is non-zero, and let us give a name to this quantity here. This is equal to minus gamma over 2 plus or minus I times omega shifted. So this is the shifted frequency or shifted angular frequency omega squared minus gamma squared over 4 square root. So we still have the possibility of oscillatory solutions, but the frequency is shifted and there is a minus gamma over 2 sitting outside. So this tells you that the solution is exponentially damped. So this would imply that x of t in general is of the form a e to the minus gamma t over 2, that corresponds to this part of the solution, times e to the plus or minus I omega s, which I could as well write as either cos omega st plus b e to the minus lambda t gamma t over 2 sine omega st. So I have solutions which are oscillatory, but with a shifted frequency, not the original natural frequency, but this combination omega squared minus gamma squared over 4 is the natural new frequency, and there is an exponentially damping factor here. This is called the underdamped case. What does it mean? It means that the solutions, if you plot the solutions, for instance, let us look at initial conditions where x of 0 is a and x dot of 0 is 0, so that this part goes away completely, and then you are left with a solution which looks like this. Here is t, here is x of t, At t equal to 0 it starts at the point A and then it oscillates with a frequency omega sub s, angular frequency omega sub s, but instead of being just a cosine curve it is now damped by this exponential. So this looks like, and this damping here, this function, the envelope function is e to the minus gamma t over 2, and this is minus the same thing. So it leads to damped oscillations. What does x dot do in such a case? Well, that is easily plotted too. Here is t, here is x dot of t, and that starts with 0, because if x starts with a cosine and there is no sine here, then if I differentiate this once I get a sine t here omega st, and that is 0 at t equal to 0, and then it is negative. So this thing which starts at A moves backwards. So you are here, you start at this point and then it does this. So again there is a damping here in this fashion. And both the velocity and the position tend towards 0 in this case. What happens in the phase plane? So the phase plot is what reveals to us what the true nature of this solution is. Here is x and here is x dot, and this is the phase plane. In the absence of damping we would have had ellipses of this kind, but now the system starts at A, but this, because of the damping, what it does is to decrease, it does not go quite back to A, and then it keeps doing this, and in an inward spiral it spirals towards x dot equal to 0 and x equal to 0. The fact that x changes sign with decreasing amplitude is precisely what makes the spiral there, and that is reflected here. X changes sign, goes back and forth, but with decreasing amplitude. So this is not an ellipse, obviously it is a spiral of some kind, it is an inward spiral tending towards 0 0. It tends towards the origin in the x plane and x dot plane, and that is under damped simple harmonic motion. There are cosines and sines. The frequency is shifted from the original unshifted frequency of omega to omega squared minus gamma squared over 4 square root, and there is an overall exponential damping factor with a characteristic time which is 2 over gamma, and that is exactly what these exponents are telling us. So this is the underdamped case in which you have oscillatory an oscillatory approach towards the equilibrium point of 0 velocity and 0 position. Okay. The next case, which is not quite so interesting, is the case when this bracket vanishes, exactly when the square root vanishes. So we have the second case where omega is exactly equal to gamma over 2. Then this bracket vanishes, the square root, and you are left with lambda 1, which implies lambda 1 comma 2 are both the same, they are both equal to gamma over minus gamma over 2. The general solution in this case obviously can't be of the form e to the minus lambda 1 t e to the lambda 1 t plus e to the lambda 2 t, for the simple reason that they are both the same solution. The general solution is of the form x of t is a e to the minus gamma t over 2 plus b t e to the minus gamma t over 2. I shall not go into how this arises, it is again a straightforward consequence of solving this equation using a proper procedure, but the fact that you have a t here makes this solution linearly independent from this solution. They are two different functions of t. On the other hand, they have the same common exponential factor on each of them, and as t becomes very large, this is not going to dominate over that. The exponential dominates, goes towards 0 exponentially fast. Although this rises, this takes care of it and things go down to 0. So this is again an exponentially damped solution, and what happens here in the phase plane is simply that you have an approach, you start at x here, x dot here, you start here, it goes up trying to become a spiral and then slowly tends towards this. It does not cross the x axis, never becomes negative, because this thing here for an initial condition such that A is positive and B is 0 is always going to be just an exponential damped quantity which has got the same sign. So x remains positive, but x dot slowly tends towards 0, both of them exponentially fast. This is the critically damped case. Oscillator. And the third case is when omega becomes less than gamma over 2, we already saw that this was the underdamped case, this one is the so called overdamped case. And what happens to the lambda 1 and 2 in this case? Lambda 1 comma 2 are both given by just that factor there, minus gamma over 2 plus or minus square root of gamma squared minus 4 omega squared, or rather gamma squared over, let's write it as square root of gamma squared over 4 minus omega squared. And please note that both of them are negative. So lambda 1 is negative, lambda 2 is negative. Both are real and both of them are negative. And the general solution, which is of the form A e to the lambda 1 t plus B e to the lambda 2 t, is a superposition of two damped exponentials, one of which is a much faster damping exponential, the one with both minus signs, whereas the one with the plus sign does not decay as fast because it is not so negative here. The picture looks pretty much like this. In fact, it looks even more damped, it will damp out even more rapidly in this case, and we are not going to be concerned very much more with this because it just says monotonically these functions x will just decay in time monotonically as t increases, and not very interesting as far as we are concerned. The underdamped case where you still have oscillations when you have a small amount of damping is physically very often the most interesting case of all. Now let us see whether we can look at another physical system which displays exactly the same sort of behavior, and this has to do with the electrical analogy which I made last time to the undamped oscillator. If you recall, we looked at electrical analogy. If you recall, for the undamped oscillator x double dot equal to minus omega squared x, we also had an LC circuit which looked like this. You had an L here and a C here, and the charge on this capacitor Q behaved like L Q double dot plus Q over C was equal to 0, since there is no applied voltage on this circuit, and this LC parallel circuit has exactly the same behavior as this equation. It is Q double dot equal to minus omega squared Q, and omega is 1 over square root of LC. We now need to introduce a damping so that the equation looks like a term with a Q dot present in it, and of course we know what Q dot is. It is the current in the circuit, and we need something, the voltage across which is proportional to the current in it, and that of course is a resistor immediately. So if I have an LCR circuit, and this is the direct analog of the damped oscillator, so this is called the LCR series circuit. We have our inductor, our resistor R and a capacitor C L. Then the equation obeyed in this circuit by the charge, initial charge on the capacitor will change as a function of time according to L Q double dot plus R times Q dot, and this is the current. And that is of course the rate of change of the current, which is what is giving you by the back EMF across the inductor by Faraday's law of induction, plus Q over C equal to 0. Now this is the exact mechanical analog of the equation we had earlier, which is mx double dot plus m gamma x dot plus kx equal to 0. So the electrical mechanical analogy goes like x, the counterpart is q, the charge q on the capacitor, the position x of the damped oscillator is like the charge q, instantaneous charge q on the capacitor. The mass of this oscillator is the analog of the inductor. The gamma, the friction constant here, which has dimensions of time inverse, the friction constant which has the dimensions of time inverse is after you divide through by m or L as the case may be, this has dimensions of R over L. Notice that L over R is the time constant of an LR circuit. So we already see this analogy appearing, and K, the analog is 1 over C, omega squared, the analog is 1 over LC. And you have exactly the same behavior for this damped for this LCR circuit with a resistor there as you have in this case. And as before, the condition for damping, over damping, etc. So we want to have under damped an under damped circuit corresponds in the earlier case, mechanical case, to omega greater than gamma over 2, or in this case 1 over square root of LC greater than gamma was R over 2F. Or so if I square both sides, 1 over LC greater than R squared over 4 L squared. So let us cancel out an L. That is the condition. So under those conditions, when you fix the R, L and C in such a way that the resistance is sufficiently small. So the way to write this is to write this as R squared less than 4L over C, 2 square root of L. So an LCR series circuit is underdamped if the resistance is smaller than twice the square root of L over C. In such a case, you are guaranteed to have an approach, the discharge of this capacitor is finally going to tend to Q equal to 0, Q dot equal to 0, will happen in an oscillatory fashion such that the charge goes back and forth and oscillates with decreasing amplitude, with an amplitude which is attenuated by this exponential factor controlled by the time constant L over R here, L over R, half of that, and that fixes the way the circuit behaves. And of course one could also look at the over damped and the critically damped cases. If you recall, when you want an instrument to point towards its final reading, you would like no over oscillations, no overshooting, because then it takes time for it to get back. You would also not like over damping because it takes a long time for it to reach saturation. So the most efficient way of arranging matters in such a case, when you want a meter to point to a final reading, is, as in the ballistic galvanometer, an ancient piece of equipment, is to make it critically damped. In other words, to fix matters such that this becomes an equality, and when that happens you have the most efficient instrument for that particular application. Now there are many other cases where you use the damped simple harmonic oscillator, and this is not just a model of damped oscillations. It is more than that, it actually serves as the basic model of dissipation in a huge variety of applications, of which this is just one. There are many others. I should mention in the same breath that if you complicate the manner in which the damping occurs, for example, if you assume in the mechanical case that the damping is proportional to the square of the velocity and not the velocity with the appropriate sign, the matter becomes immediately much more complicated. Or if you assume, for instance, that the friction is like dry friction and not viscous friction, so there is a threshold over which it does not it acts as a frictional force, and after that there is no frictional force at all once the threshold is crossed, then you have yet another complication and the matter is once again not so trivial at all. So there are many complications which you can add on to this, but this simple damped harmonic oscillator serves as a basic paradigm of damped of dissipative motion, of motion where the total energy is not conserved, of oscillatory motion which slowly gets damped towards 0, and the underdamped case in particular is of great significance in practical considerations and applications of the oscillator model.